So we ended with the discovery of strange particles like the kaons and baryons, and we showed that these strange particles usually were produced always in pairs, and then they had unusually large lifetimes. And we also showed that it was also experimentally seen that strangeness is conserved in strong interactions as well as in electromagnetic interactions. So this leads us to the motivation of introducing a new quantum number called the hypercharge. Suppose even before we go about motivating the strangeness, suppose if you look at the multiplets in an isospin group. So the multiplets in an isospin group are characterized by the electric charges. So you will see that the highest isospin state in the multiplet has a charge which is Q max. And then if you go down, the charge reduces and then you go to the Q min, which is the minimum charge of the lowest state in the multiplet, in the isospin multiplet. So suppose we studied this multiplet on pions. So that was symmetrically placed about the q equal to 0 axis because the pi 0 state was in the center with the charge 0, and the pi plus and pi minus states were on both sides of the q equal to 0 axis symmetrically placed with equal isospin components I3. However, sometimes you have states like this delta, which has there are 4 such degenerate states, and they have a charge +2, +1, 0, and -1. And they are not placed symmetrically about the q equal to 0 axis. And this usually happens when in a multiplet, the sum of the maximum and the minimum charges are not equal to 0. For the pion, of course, the Q max was 1 and the minimum charge was -1. So the sum of the maximum and minimum charges was 0. So it was symmetrically placed. Whereas for these delta multiplets, the charges maximum and minimum do not add up to 0. And that's why these states are not placed in the isospin plane symmetrically about the q equal to 0 axis. So then what do we do here? So analogous to what we usually calculated classical mechanics about the center of mass, similarly one can introduce something called the center of charge of any multiplet, which is defined as the hypercharge. So the hypercharge is defined in this manner that y by 2 is defined as the average of the total charge in the multiplet. So once you have this hypercharge, then of course one can show that charge of any member of the multiplet can be written in terms of this hypercharge and the isospin component I3. And this was the famous formula by Gell-Mann and Nishijima. You can check this for these kind of isospin states like the delta or the pion, and you can convince yourself this relation works very well. Now the interesting part that you should realize is that it was argued that this hypercharge actually can be written in terms of different other quantum numbers, like we introduced the baryon number, the strangeness, etc. So hypercharge is the sum over baryon number and strangeness. And I wrote ... because later on there were many other quantum numbers discovered like the charm and etc. So you can add them up all. And the interesting part is that all these baryon number and strangeness, these are conserved in strong interactions. So is the hypercharge. So this is how the strangeness enter into the picture through this hypercharge. So now, since you have a new quantum number, the interesting part of it, you should realize that if you look at this formula, then any charge of any particle in a multiplet, isospin multiplet, cannot be uniquely determined only by the isospin component I3. So you need two quantum numbers. If you see this formula by Gell-Mann and Nishijima, that you need two quantum numbers, I3 and the Y, which is the hypercharge, to characterize the charge of the states in a multiplet. So this tells you already that in order to denote the states in the multiplet, you need two quantum numbers, I3 and Y. And that's how you can characterize the states. But in quantum mechanics, you know that any state, a quantum mechanical state, can be characterized by the eigenvalues of commuting Hermitian operators. So that tells you that in order to represent the hadron states, one needs two Hermitian operators which commute with each other, and the eigenvalues of them will give you the I3 and the Y. Now SU2, as we discussed, the SU2 symmetry group only has one diagonal element, which was this I3. So we use this to characterize the states of the SU2 multiplet, isospin multiplets. So now, in order to have two such commuting observables, the easiest extension is to go from SU2 to SU3, because the SU3 group, you can show that it has two commuting generators. In fact, if you look at the textbook, it's the most general construction that any SU3 group, or in the fact that any SUN group has n square minus 1 generators. So SU3 group will have 8 generators, which are denoted by this Fi's, which are matrices, and they satisfy this following commutation relation. This Fijk is a structure constant which is antisymmetric in the exchange of these indices ij and k. And this I, j, k, these run from 1 to 8. So you can see any standard textbook on group theory or even particle physics, and you can see the structure of these Fs. And also you can construct it by yourself. So you should remember, this is your assignment, that SU2 is a subgroup of SU3. So we know that these Pauli matrices were the generators of SU2. So now you have to generalize those Pauli matrices, because SU2 is a subgroup of SU3. And out of the Pauli matrices, using that as a template, you should construct all these generators for SU3, which we denote here as Fs. So once you do that, you can see that there are two generators of SU3 which are diagonal and commute with each other. And those are this F3, which also I call as I3, the operator which projects onto the third component of isospin. This is the generalization of the sigma 3 matrix that we did. So sigma 3 is this 2 cross 2 component, and then rest are 0. And this Y, which is like a hypercharge, it is defined conventionally in this manner, F8 by square root 3, and you can show that this is of this form. This is also diagonal of this manner. And since they are diagonal, they commute with each other. And so for characterizing any quantum mechanical state, you need complete set of commuting observables, which are this I3 and Y, and then use the quantum numbers of these observables to characterize the states. So this is the general program. Now you can show that there are 3 different SU2 sub-algebra of the complete SU3 Lie algebra. So in fact, if you look at the generators, as I mentioned, there are 8 generators, F1 to F8, out of which F3 and F8 are diagonal. So we use that to construct the states from its eigenvalues. And then you're left with the 6 others. So you can construct the isospin raising and lowering operator I plus minus in terms of F1 and F2 in this manner. Similarly, there is something called the U spin. So it is similar to isospin. They are also generators of another SU2 subgroup. And then you can write this U spin up and U spin down in terms of these two generators of the complete SU3 group. And the third SU2 subgroup subalgebra is satisfied by this generators V plus minus, which is constructed out of the F4 and F5. This fourth and fifth generators of SU3. Now, what do I mean by the statement that these I, U, and V satisfy the subalgebra? So this I is the isospin. So this is the SU2 part of the SU3, and they represent the isospin that we were discussing in the earlier lecture. And when I mean, what is the meaning of this SU2 subalgebra? So you can explicitly show that I plus commutes, doesn't commute with I minus, but the commutator is given by 2 times I3. And exactly you can construct similar commutation relations with the U and the V spin matrices. So they have identically same SU2 subalgebra. And you can also show that this U3 is related to the hypercharge and isospin in this manner with this relation here. And then similarly, V3 is also related in this fashion. You can look at the matrices. All these F matrices construct the V3 and U3 from these relations and then construct, arrive at this relation. And also, you should also note that one needs to also see how these individual SU2 subalgebras relate to the diagonal generators. So you can see that the commutator of Y with V plus minus gives you plus minus times the V plus minus operator. So if you have a state and act V plus minus on it, then you can see that its hypercharge is increased or decreased by a unity using these relations. And also using the second relation in the last set of equations, you can show that if you act V plus minus on your state, then the isospin increases or reduces by half. Whereas if you look at, so similarly you can construct for U spin also. I only wrote for the V spin, but you can also do it for the U spin. Only the sign gets modified a bit. And the interesting part to note is this third part of the last set of equations, that the original isospin group is not affected by the hypercharge. So if you look at the isospin states, its hypercharge is exactly 0 using this because it commutes, I plus minus commutes with the hypercharge. Okay, so are there any questions till now? I'm just using the results, SU2 results that we had in the last class.
Hello, sir.
Yes.
Sir, what are the use of these shift operators, U plus minus,
Yeah,
V plus minus?
I will discuss this right now.
Okay, sir.
They are very important, and that helps you in identifying many properties in the quark model that I will come.
Sir, can you tell the commuting operator Y and I3? They are commuting operators, so that they have same eigenstate. Then
yeah, they have same eigenstate, which is given by this. And if you look at the first bullet point, so this same operator say they have same eigenstates and characterized by these quantum numbers, which are eigenvalues of this operator I3 and Y. This is what you do in quantum mechanics. So you calculate, to get the physical spectrum, you calculate all possible sets of commuting operators, and then once you get the commuting operators, then your physical states are the simultaneous eigenfunctions of these operators, and then you use the eigenvalues of these operators to label your state. So that's how I labeled the physical states with I3 and Y.
Yeah, that's what I want to know. How we can do these two commuting operator to taking same label, that Y into I3.
Yeah,
First,
so that is, as you know, in quantum mechanics you learned, right?
yeah.
So to label a state, any physical state, you need the eigenvalues or the quantum numbers of the set of commuting observables or operators, Hermitian operators. So here the set of, there are two of them, I3 operator and Y operator. So you take the eigenvalues of these operators to characterize your state.
Okay.
Okay. So moving further, so now how do we diagrammatically represent my states? So one way, so as we discussed from the question that was asked right now, so any physical state has to be represented in with two quantum numbers, the hypercharge Y and the third component of isospin, which is I3. So you have to represent all the states in this two-dimensional axis, with the y-axis as the hypercharge and the x-axis as the I3. Because those are the quantum numbers which you know and which you will use to characterize the states. Now we had these three sub-algebras. So those can be denoted by these different lines. So for example, we showed that if you look at the last point, U3 is related to Y and I3. So what will be the U3 equal to 0 axis? That is the axis where your third component of U is 0. So that is given by this red line. And similarly, V3 equal to 0 is given by this orange line. Because here, if you use the relation in the last slide, then the hypercharge is minus 2/3 times the I3. So you can draw these lines in this Y and I3 plane. These are just straight lines. You can draw them passing through the origin of this plane. And of course, since I3 commutes with, the I3 equal to 0 line is nothing but the line vertical axis. So you can see that the lines, orange line, red line, and the gray line here, this is the I3 equal to 0 line. They are all at 120 degrees to each other by construction. And from the, so for these, we only use the relations that come out from the forms of these matrices. And that is dictated by the symmetry group because they are generators of your SU3. So as I discussed, all these axes where U3 is equal to 0, V3 is equal to 0, and I3 equal to 0, they lie at 120 degrees to each other. And because of the equivalence of these three subalgebras in this isospin and hypercharge plane, you can show that any multiplet or the states, SU3 states, should be regular hexagons or triangles because of this symmetry. And because because you should note that any SU3 multiplet, all the states in the SU3 multiplet should also be the states of the subalgebras U, V, and I. And that's why, and since the U, V, and I axes are angled at 120 to each other, so only way you will have the states is in form of regular hexagons or triangles. So once you know that, then you can construct the lowest irreducible representation of SU3 in this plane. So as again, you know that your physical states are characterized by these two quantum numbers, y and I3. So y is in the, this is written as the y-axis. So there is nothing to do with the physical y-axis. This is in the SU3 space. And this y is the hypercharge. And this I3 is the x-axis that I plotted here. So any fundamental representation of SU3, that is the lowest possible symmetry multiplet that is invariant under SU3, is of this form, a triangle. Because as we argued, all these states should be either looking like a triangle or a hexagon. So if you construct the states, then you can show that the lowest possible state is like a triangle. So what are the vertices of the triangle? So you should remember that the smallest isospin that we studied representation is the isospin equal to half. That is the smallest one you can get. We studied an example, the neutron-proton system. So the minimum representation is I3 equal to half. And this has two projections, I3 equal to +1 and I3 equal to -1. And that constitutes this vertical line on the top. Sorry, the horizontal line on the top, which is parallel to the I3 plane. So this is the isospin multiplet. Now, what is this line then? This line that goes along, that drops down here. Sorry, I should. Yeah. So what is this line here? So there are three lines. So can anyone answer what is this line that goes from, sorry. That goes from this isospin 1 state to the isospin 0 state.
That is V minus state.
Yeah, so you will see that this runs in this manner. So it is U3 equal to 0 state. So these are multiplets of V. Yeah. And similarly, this is the V3 equal to 0 state. And why we consider all these things? Because they all are subgroups of SU2. So you need the smallest representation of all the U, V, and isospin doublets. So since isospin, the lowest representation is a doublet, so you see that there are two states correspond to the isospin I3, also two corresponding to the V3, and the two corresponding to different components of U3. So till now I have not used any further arguments to construct all of these states, except symmetry properties of your system and basics of quantum mechanics. Now let's denote these states as psi1, psi2, and psi3. I call them. So I wrote it in a bracket notation in this manner. So this one, the rightmost one is psi1, this is psi2, and this is psi3. So I3 acting on psi1 and psi2 should give you, sorry, here I missed a factor of half. So psi1 and psi2 are these isospin states, half and minus half. So I3 acting on these two states will give you plus minus half times psi1, 2. And this psi3 is this bottom state here. So the isospin is 0 because it's isospin singlet. So that is 0. Also this psi1 state here in the rightmost side, as we argued, this is the state with U3 equal to 0. So if you act U3 on psi1, it should be 0. Now you know what is U3 because we showed here that U3 can be written in terms of Y and I3. So then using this fact, you can show that psi1 has a hypercharge of 1/3. So you can use this relation here. U3 is 3/2 y minus I3. And as you know, the I3 quantum number of this state psi1 is half. So you can show that the hypercharge quantum number is 1/3. So that's why I wrote this state as I3 equal to half and y is equal to 1/3. Is this argument clear to everyone, or if there are questions, I will wait for it. Okay, so then you can use similar construction here, because this is V3 equal to 0 state, and get the hypercharge here. And what do you use to get the hypercharge of this state? Hello? How do you construct the hypercharge of this last in the apex of the triangle, the state? Anyone? Yes? Try. So as you can see, these two states lie on the U3 equal to 0 axis. So you can act V minus on this state to go from here to here. So these are V spin multiplets. So you can use those, and we introduce the notations for V minus and V plus, and then you can show that indeed the hypercharge of this is minus 2/3. Now,
excuse me, can I ask a question?
Yes.
Yeah, so basically, I think I got the point as to how we're going from one state to another. For example, let's take the right-hand side edge and we're going to the apex. So explain that we're acting basically by the operator V negative, and that's how we make this transition. But I don't really follow the argument about something U3 axis being 0. Like, I don't understand how does that relate to this V3.
Oh, so psi1, which is the rightmost corner of the triangle, that lies on the U3 equal to 0 axis. So, and then U3 is related to the hypercharge and isospin in this fashion in the last equation. So you can use this relation and show that the hypercharge of psi1 is 1/3. This is just to derive the hypercharge of the particles.
Okay, all right, I got it. Yeah. Okay, thank you.
Okay, welcome. Okay, so then once we know the isospin and hypercharge, you know the Gell-Mann and Nishijima formula. So you can calculate the electric charge, which is given in terms of these two quantum numbers, I3 and Y, which is I3 plus Y/2. And then you can construct the charges, electric charges of these states. You can show that this rightmost part, which is the psi1 state, has an electric charge of 2/3. And these two states on the leftmost side and the apex of the triangle has a charge minus 1/3. These are the electric charge. So it tells you that the particles which constitute the fundamental representation of SU3 have fractional charges. And that led to Gell-Mann naming them as quarks, and Zweig called them as aces. So these representations were arrived at only from symmetry considerations. And at that time, there was no experimental confirmation of the quarks. So later, of course, one discovered it, and I will discuss a bit of that and also in the other lectures. But this is one of the very profound impacts of theoretical particle physics, that you can use symmetries to determine a lot information about your quantum systems. And of course, if you have this representation, this is called a 3 representation. I wrote it in green here. And these are for, suppose you call them different quarks. So you know this 2/3 charge is carried by the U quark and minus 1/3 by the D and the S quark. So you can think of these states as the UDS states. And of course, since they are fermionic species and they have different quantum numbers, so they will also have another representation where all these quantum numbers are negative of each other. So that is called the 3-bar representation, and that corresponds to the anti-quarks or the anti-fermions. And also that you can argue from the symmetry group SU3. The SU3 has 2 distinct fundamental representation, unlike SU2, because SU2 has only one pseudo-real representation. So then you have 2 representations of SU3. I only showed one of them, the 3 representation. There is also 3-bar, which is an inverted triangle. And with quantum numbers all negative of what I wrote here. So that corresponds to the antiparticles. And these are the 2 different, lowest irreducible representation of SU3. Now, why are we doing this? So when in the end of 1940s, beginning of 1950s, there was an exciting time in particle physics. So initially, people started discovering new particles in this using photoemulsion techniques, and then of course cyclotron. There was cyclotron which was installed in different places like in Berkeley, in California, in Chicago, and different places, and they started finding out lots and lots of particles. They termed it as baryons and mesons. Baryons being the having spin, half integer spins, and mesons having integer spins. And there are lots of them discovered in a very short span of time. So that led to this terminology called the particle zoo. Now the question was that are all these particles very different from each other, or there's some way of characterizing them or bookkeeping them? So that was actually first done by Gell-Mann, and then that goes by the name of the quark model. So what is the idea? So as we discussed, we know the fundamental representation of your SU3, and then can we construct the baryons and mesons out of these fundamental representation? So for that, of course, you need some experimental input. And then the experimental input is that for mesons, which are all with integer spins, and most of them that were discovered at that time were spin 0, pions and kaons and all. So then they have these isospin, and it was observed that the particles and antiparticles are members of the same SU3 multiplet because they carry the same spin. And they have baryon number 0. So then, whereas the baryons actually have half integer spins, so that tells you that they should be constructed out of odd number of quarks. However, since mesons have baryon number 0, they are their own antiparticles. Sorry, the antiparticles are the members of the same multiplet. So then the only way to do is you have a 3 representation that we showed, and you do product with the 3-bar representation. So this is, so then once you do this product rule, and you can find out the states which come out of having a Q and a Q-bar representation. So how to, there are various ways to do that. There are group theory techniques which you learn, but I will only outline a simple way to do this. So you know this green triangle here is the 3 representation. To have a operator product with the 3-bar representation, what you do is you put the So the 3-bar representation is just the inverted triangle. So these are these orange triangles. So to get this product states, what you do is you take the original 3 representation, which is given by this green triangle, and in the each vertex of this green triangle, you put in the center of the other representation, or the centroid, because so if you see here, I had the 3 representation, which is the green line. I go to the center of this, the one of the edges of this, the green line, and put in the 3-bar representation, which is given by this orange triangle, with its center based on this point. And similarly, I follow the exercise for all other 3 vertices of the original 3 representation. So then the resultant figure that I will get is a hexagon, because there will be states here, here, here. There will be 3 states here. There will be 1 state here, and also one each in the bottom. And then I joined everyone with a red line. So that will give you a hexagon. So now you can show that, so you multiply 3 states with another 3 states. So you should get 9 in total. And 8 of them form a hexagon, which is the 8 representation, or the octet as we call, meson octet. In the center of it, there are 2 states, and there is another state which is a singlet, which is not a part of this hexagon. So this is one of the simplest way to construct this. And as I mentioned here, the center has a 2-fold degeneracy for the octet. And then you can, when you do this thing carefully, then you can see that there are 2 states on the top part of the hexagon, which has isospin projections +½ and -½. And they were identified to be K plus and K0. If you look at the quark content, then you can see that these 3 states, which has hypercharge 0 and isospin 1, 0, and -1, they are pions. And of course, there is another particle called eta, because there are 2 in the center. And these lower ones are the K- and K0 bar. You can construct all of these if you take whatever you have from the fundamental representation and do the product in this diagrammatic manner. Are there any questions here? Hello?
Hello, sir.
Yes.
Sir, how do you recognize it is meson octet, not baryon octet?
Oh, because I multiply with the 3 with the 3-bar state. So I have a quark and an anti-quark. And then you can show that this has a baryon number 0, because quarks carry some baryon number, and the anti-quarks carry the equal and opposite baryon number. So the net baryon number is 0. So this is the meson octet.
Okay, sir.
Yeah.
So can you please explain this 3 multiplication with 3 bar, how we can decompose it into 8 plus 1? Can you explain?
Yeah. So yeah. So first of all, did you understand how to do the 3 cross 3 bar multiplication?
The method which you explained, yeah, with the triangles.
So you take the 3 representation, which is the green, and on each vertex you put the center of the 3-bar representation, which are these triangles.
Yes.
You will get all these states, which are given by these orange crosses. These are the vertices of this orange triangles. So that will give you the final states. So you can show that you will have 2 states with isospin half and -1, -½ and hypercharge 1 on the top. And then there will be states here and states below. And you can, so I didn't explain it, but if you look at the representation theory of SU3, you can show that the outer layer of, so we discussed that the representations are either hexagons or triangles. So there will be, this is a hexagon, and whenever you have a hexagon inside that, so on the hexagon you will have only one state at each point or each vertex of the hexagon. If you go inside the hexagon, then you will have at most two states. So that's why the center has a twofold degeneracy. So in that logic, you can have only total 8 number of states within the hexagon. This comes from group theory multiplication rules. And then since you're multiplying 3 states, so your product space will have total 9 states. So this one is a singlet, which is not a part of this. It's a separate one, which is orthogonal to all of these states. Is it fine with you?
Yes, sir.
Okay. So similarly, you can construct baryons, as baryons are spin half particles or spin 3 half integer particles. So they consist of 3 quarks, because the only way to construct half integer, because each quark also carry half integer spins. The only way you can combine to get half integer spin out of quarks is to have 3 of them. And you can follow the diagrammatic rule that I mentioned earlier. And you can show that 3 cross 3 cross 3 gives you a decuplet, which is the 10 representation, and 2 octet representation, and a singlet one. So here I draw the decuplet or the 10 representation. So you can, if you follow the calculations and do the product properly, then you can show that you will get these states. So on the top with hypercharge 1, you have the delta. There are 4 of them. And then there is the sigma star, which corresponds to hypercharge 0. And there is a hypercharge -1, which are the cascade states. And then you have this omega minus. So at that time when Gell-Mann predicted this quark model, then this particle was not experimentally discovered. This was a prediction from theory, and later on it was confirmed from experiments. So that tells you the success of the quark model. So this omega minus, if you do the product carefully, it consists of 3 strange quarks, and that should make you a little bit alarmed, because if you look at the spin, I didn't tell anything about the spin of the particles here. If you look at the textbook, you can see how they also consider the spin, because all of these are spinors. So you will see that these kind of particles have the same quark with the same spin. But you know, Pauli exclusion principle tells you that you cannot have fermions, 2 fermions with the exactly same quantum number sitting on the same state. So from here, people started thinking. So first time it was, I guess, predicted by Oscar Greenberg, that there should be some other quantum number called color, which will allow such states to exist by satisfying the Pauli exclusion principle. So you need an additional quantum number called the color. And this is also, I would say, a byproduct of the quark model, because when you started looking at the quark model, you construct states, and then you see the need of additional quantum numbers from it. And of course, then color, the theory of color leads to quantum chromodynamics, and there are a lot of so many implications of having a color charge, and that is what you all will work on in your research life, to understand the dynamics of color charges. Okay, so let us look at the octet that we constructed. So as I mentioned, so if you have 3 quark states, if you do the product rule properly, then you will have decouplet, which I showed here. And also there will be this octet states. So one of the octet states is this one. So on the top, you have a neutron and proton. So these are isospin states, isospin half states. So a green line is the I plus, which is the raising operator in the isospin space. So if you go along this direction, you increase your isospin by +1. And similarly, this sigma axis, sigma plus, sigma 0, and sigma minus. Also, there is another particle here, lambda 0. They are also isospin triplets. So you can act I minus on it. And if you look at the particle data book, then you will see that the mass difference between the neutron and the proton is about 1 MeV. And similarly, the mass difference between these states, sigma plus, sigma minus, etc., is maximum 8 MeV. And also this lowest isospin state, this cascade, the mass difference is only 7 MeV. So this tells you that these isospin states are almost degenerate. They are not exactly, but almost, because the mass difference is very small. And why am I calling it small? It is small because if you compare it with the mass of the particle, like the proton is around 1 GeV, the mass splitting is very tiny. It's almost like 3 parts, 10 to the minus 3 times 1 GeV. So the relative mass shift is very tiny. So isospin is very well conserved, I would say. This red line here, this is the U spin axis. So similarly, the green line is the isospin states. So similarly, the red line are the U spin states. Now, if you look at the U spin states, what do you see? What is the electric charge of these states? Like the neutron, you have the sigma 0 and the cascade 0. So what are the electric charges here?
Neutral, 0.
Yes, they're neutral. So if you look at the U spin states, you will see that all of them have the same charge. So that tells you that the U3 commutes with the charge operator. And you can also show it from the relations that we have earlier. And also this central state is, it is 2-fold degenerate, but you can show that it cannot be an eigenstate of U spin. So you can show that you can make a combination of these two particles, sigma and lambda, and then this combination is, this chi is an eigenstate of U spin. Now U spin is very badly broken. So if you go along this axis, red axis, then the mass difference is of the order of 100 MeV. So neutron is like 939 MeV, and the cascade is much higher mass. So the mass splitting along the U spin direction is very, very large. That tells you that U spin is not very well preserved symmetry of SU3. However, if all the symmetries were preserved, then all the states in this octet should be having the same mass. Whatever differences happen due to small breaking of these U or isospin or these SU2 subgroup symmetries. And then if you use the fact that the states along the U spin axis have the same charge, so then you can show that the corrections due to electromagnetism are same for all of these particles, the U spin states. And then using that fact, you can arrive at this relation, which is called the Coleman-Glashow relation. It gives you the relation between neutron, proton, and all of these masses. And your assignment should be, you should look at the particle data group and then check the masses and see whether this relation holds good. You will see that this relation holds good to quite a good extent. So the U spin is not a very good symmetry, but you can still get some useful relation using the U-spin multiplets. And of course, as I already mentioned, since you construct these octet or decuplet states, all of these states from multiplying these fundamental quark states, you should realize that your fundamental representation consists of U, D, and S quarks. So they are not exactly degenerate. So their masses are not exactly the same. So the isospin symmetry is not exact. Moreover, there are effects of electromagnetism also. So if one takes into account all of these corrections, then one can arrive at the formula for the masses of the particles in these multiplets. So that is the famous mass formula of Gell-Mann Okubo. I am not going to the details, but you can derive these using the fact that the amount of isospin symmetry breaking is small, and then you can write whatever is the breaking term. So if you look at this formula, the mass is given by some constant A. So suppose all the particles, if SU3 was an exact symmetry, then all the particles will have a mass of A. But since SU3 is broken by the isospin is also not exact. So then all these correction terms come. And using these kind of formula, you can show some useful relation, like you can show that the mass of neutron plus mass of this cascade zero particle is related to the mass of lambda 0 and sigma 0 in this form. This also you should verify using the data from particle data booklet for these masses. So this is called the Gell-Mann Okubo mass formula. This also is one of the predictions that come from the quark model. Okay, so I end here. So I tried to emphasize that knowing the symmetries, you can construct a lot of information about the particles that constitute the standard model. And that's what I had been doing for the last two classes. So if you have any quick questions, I will answer, or I will end here today. Anyone? Okay, so then I will stop sharing, and thank you very much.
Okay,